Welcome back to the deep dive. I hope you are sitting down for this one, or at least somewhere where you can safely space out for a second, because today we are tackling a subject that literally keeps physicists and philosophers up at night. I'm talking about time travel.
And we are not talking about the fun, breezy, let's go see the dinosaurs version of time travel.
No, absolutely not. Before you roll your eyes and think we're just going to talk about DeLorean cars and flux capacitors, I need you to just look at the stack of research we have on the table today. It is
It had
heavy. It is intimidating.
Yeah.
We have papers here that look like they were written in an alien language.
It's heavy, and it's incredibly dense. We're moving way past the pop culture surface level here. I mean, we are looking at sources ranging from the Stanford Encyclopedia of Philosophy's entry on time travel and modern physics
Right.
to detailed breakdowns of decision theory like Newcomb's problem, and even transcripts exploring the narrative paradoxes that have plagued storytellers for a century.
Exactly. The mission for this deep dive is pretty specific. We want to move beyond the simple, what if I go back and kill my grandfather question, though we will touch on that because you kind of have to.
You have to.
But the real goal is to get into the real structural problems. We're talking about the hard physics of closed time-like curves or CTCs, and the genuinely mind-bending solutions that researchers have proposed to keep the universe from collapsing into a logical nightmare.
And what's fascinating to me, and what I think we'll really get into, is that when you actually look at the math, specifically in general relativity and quantum mechanics, the solutions to these paradoxes are often stranger than the paradoxes themselves.
That's what I've heard.
It turns out the universe might be okay with time travel, but the price we pay is giving up some very cherished ideas about free will, causality, and maybe even the nature of knowledge itself.
That is the aha moment I am chasing today. Because usually when we think of time travel, we think of it as a magic trick. But these sources, they treat it like a geometry problem.
It's all topology.
So let's unpack this. We have to start with the classics, just to set the stage. The can you break the past paradoxes.
Right. The destructive paradoxes, the ones everyone knows.
The most famous one, the one everyone brings up, is the grandfather paradox. But I want to walk through it slowly because I think we often skip over just how weird the logic loop actually is.
Okay, let's set the scene. You build a time machine, you're angry, or maybe just incredibly curious and devoid of ethics. You travel back to a time before your father was conceived. You find your grandfather.
A bit morbid, but stick with us. You're standing there. You have the weapon. You have the intent.
The logic trap is immediate. If you kill your grandfather, your father is never born.
Okay.
If your father is never born, you are never born. And here's where the headache starts. If you were never born, you never built the time machine, you never traveled back,
You never pulled the trigger.
you never pulled the trigger. So if you don't pull the trigger, the grandfather lives, which means your father is born,
Which means I'm born.
which means you are born, which means you build the machine, go back, and you're standing there again, ready to pull the trigger.
It's a perfect, inescapable circle.
It is a closed loop of logical impossibility.
Yeah.
It's not just that it's difficult, it's that logic itself breaks down. The event A leads to not A, and not A leads right back to A.
It effectively negates its own cause. It feels like the universe should just display a blue screen of death at that point. Like the simulation just crashes.
Precisely. And it exposes this direct conflict between causality, the idea that cause leads to effect, and the presumed free will of the traveler.
Right.
If you are standing there with a weapon and a time machine, and the laws of physics say you are physically present, what stops you from pulling the trigger? Is there a force field?
Does the gun jam?
Does the gun jam? Does a bird fly in the way? That is the question that haunts this entire field.
And there's a variation of this that I found in the sources, the self-erasure paradox, which feels a little more noble but is just as problematic. This is the scenario where you go back to prevent a war or cure a disease.
Oh, this one is tragic because it implies that success is impossible. Let's say you travel back to 1918 to stop a pandemic. You have the cure. You distribute it. You succeed. The pandemic never happens. History is rewritten.
Okay, so I saved the world. What's the problem?
The problem is motivation. In the future you came from, the new future, there is no history of that pandemic. It never happened. It's not in the history books. So why would you build a time machine to go back and stop something that never happened?
Oh, I see. By fixing the problem, I remove the reason for the fix.
Exactly. If the pandemic didn't happen, you don't go back. If you don't go back, the pandemic happens. It's the same loop. just with good intentions.
Wow.
And this leads to what some sources call the memory paradox. If you somehow did manage to do it, you would essentially be a ghost. You would remember a timeline, a history of suffering and disease that physically no longer exists.
So you're walking around with memories that have no causal link to the reality you're standing in.
You've become an anomaly, a living contradiction.
That links directly to the butterfly effect, doesn't it? The idea that you can't just change one thing.
Yeah, the butterfly effect is usually framed as chaos theory. Small changes leading to massive, unpredictable outcomes. You know the Ray Bradbury story, A Sound of Thunder?
Right, the guy goes back to the dinosaur age, steps on a butterfly, comes back, and the spelling of the English language is different, and a fascist is president. It's the classic example.
Exactly. But in the context of serious time travel discussion, it just highlights the sheer difficulty of fixing history. The traveler cannot predict the ripples. You save one life in 1918.
And what?
And maybe that person's great-grandchild becomes a tyrant. Or maybe saving that life leads to overpopulation in a specific region, which leads to a resource war 20 years later that kills millions.
So you might go back with the best intentions to save 1,000 people and end up killing 1 billion.
The chaos makes the outcome of any interference impossible to calculate. You are throwing a rock into a pond and trying to control every single ripple. It's impossible.
So those represent the destructive paradoxes, trying to break the past. But the sources highlight a different category that I find even more brain-melting. The loops of creation, the bootstrap paradox.
Yes. This is where it gets really interesting because this paradox doesn't involve changing the past. It involves the origin of information. It involves things existing without ever being created.
The classic example involves Shakespeare.
Right.
Okay, walk us through the Shakespeare scenario. This one is my favorite because it feels so technically possible if time travel existed.
Okay, so imagine a time traveler who is just a massive Shakespeare fan. He loved the plays. He's memorized them. He packs the complete works of William Shakespeare, a nice bound volume, into his time machine and travels back to 16th century England.
So he lands in London, finds a pub, and looks for the bard.
Right. He finds a young, struggling Will Shakespeare who hasn't written a single play yet. Maybe he's just an actor. Maybe he's struggling with debt. The traveler hands him the book and says, "Here, copy this. Trust me, it's going to work out for you."
Shakespeare takes the book, realizes it's brilliant, copies it, and publishes the plays under his own name. He becomes famous. History plays out exactly as we know it.
And centuries later, our traveler buys that specific book, the complete works, to take back in time.
It seems like a perfect loop. Everyone is happy. Shakespeare is famous. The traveler gets to meet his hero. But who wrote the plays?
That is the question. Shakespeare didn't write them. He copied them from the book the traveler gave him.
And the traveler didn't write them. He bought the book that was copied from Shakespeare.
Right. So where did Hamlet come from?
The plays exist without an author. The information, the genius of Hamlet, the to be or not to be speech, it exists in a closed loop with no point of creation. It just appears.
It is what we call an ontological paradox. An object or piece of information exists, but it has no origin. It never had a moment where a human mind conceived it. It's free lunch information.
That is deeply unsettling. It's like the universe got something for free.
Hmm.
The sources also mention the unwritten book or the notebook paradox, which is the same concept but for science.
Right. Imagine a scientist is struggling to invent the time machine. Suddenly, her future self appears, hands her a notebook with all the equations, and leaves.
So she uses the notes to build the machine?
He builds the machine.
Uh-huh.
Then, years later, she travels back to hand the notebook to her younger self. The knowledge of time travel was never discovered. It was never derived. It just exists in the loop.
And it gets worse when you apply it to physical objects. This is the issue of infinite regression. The example given in the notes is a watch.
Yes. So I travel back and give my grandfather a watch. He keeps it, wears it for 30 years, hands it down to my father. My father wears it, hands it down to me. I then travel back and give that exact same watch to my grandfather.
Okay, so the watch is just going in a circle through time, no big deal.
But think about the second law of thermodynamics, entropy.
Oh, things wear out.
Things wear out.
Yeah.
Every time the watch goes through the cycle, grandfather, father, son, back to grandfather, it ages. It gets scratched, the gears wear down.
So if it goes to the loop infinitely.
It should disintegrate, it should turn to dust. But if it turns to dust, I can't give it to my grandfather in working condition. So does the loop somehow reset the entropy of the watch? Does time travel repair the watch?
Or does the watch have to be made of some magical material that doesn't age?
It suggests that for a physical loop like this to work, the object would have to be immune to the ravages of time, which, contradicts everything we know about physics.
Or it implies that the loop isn't truly infinite, which breaks the logic again. This leads us to the darker side of loops, the predestination paradox. This is the you can't fight fate scenario.
Right. This is where your attempts to stop an event actually cause it. The classic Greek tragedy of Oedipus Rex is the prototype trying to avoid the prophecy is exactly what makes the prophecy come true.
And in modern sci-fi, The Terminator is the perfect example. I love that movie. But break down the paradox for us.
So, Skynet sends a Terminator back to kill Sarah Connor to prevent the birth of John Connor, the resistance leader. The humans send Kyle Reese back to protect her. But Kyle Reese falls in love with Sarah and becomes John Connor's father.
So if Skynet hadn't sent the Terminator,
The humans wouldn't have sent Reese.
and John Connor, the threat Skynet was trying to eliminate, would never have been born.
Exactly.
Yeah.
The future depends on the past.
Yeah.
But the past only happened because of the future. It's a causal loop. Skynet created its own enemy.
It suggests that in a universe with time travel, free will might just be an illusion. You think you are choosing to go back to change things, but you are just playing your part in a script that is already written.
You're a puppet on a string, and the string is time itself.
That's a very poetic and very depressing way to put it. Okay, so we've established that logic hates time travel. It creates nightmares for causality. But let's pivot to the hard science. Because our sources, specifically the Stanford Encyclopedia of Philosophy entry, make it clear that physics doesn't necessarily hate it.
Not at all.
In fact, general relativity seems to leave the door wide open.
It does. And we need to introduce a term here that kept popping up in the reading. Closed time-like curves, or CTCs.
It sounds technical. Can you break it down into plain English for us?
Sure. In general relativity, gravity isn't a force like magnetism. It's the curvature of space-time. Matter tells space how to curve. Space tells matter how to move.
Right.
A physicist named Hermann Weyl observed something strange. He realized that if you curve space-time enough, say, with a rotating black hole or an infinitely long rotating cylinder, the geometry gets twisted.
Twisted how?
Specifically, the future and past light cones can overlap.
Okay, light cones. We need to visualize this. What's a light cone?
Imagine you turn on a flashlight in a dark room. The light spreads out in a cone shape as it moves forward away from you. In physics, we use this to map causality. Your future light cone is everywhere you could possibly go or influence, limited by the speed of light.
And the past one?
Your past light cone is everything that could have influenced you. Usually these point in opposite directions. Future is forward, past is backward. Simple enough.
But with a closed time-like curve?
A time-like curve is just the path an object takes through time. If it is closed, it means the path loops back on itself. You are moving forward in your own personal time. Your watch is ticking forward. Your heart is beating forward. But the geometry of the universe is curved such that your future leads back to your past.
So it's not magic, it's topology. It's the shape of the road. If the road loops, walking forward brings you back to where you started.
Precisely. You don't need a flux capacitor, you need extreme gravity. And this is where we get a potential solution to those paradoxes we just talked about. This comes from the work of physicists and philosophers like Wheeler, Feynman, and Maudlin. They looked at the topology of these loops and asked, is a paradox inevitable?
And they used the gray film argument, right? This one really stuck with me because it's such a specific visual, it feels like a detective story clue.
It is a beautiful argument. Imagine a camera pointed at the exit of a time machine. It is set up to take a photo of whatever comes out. The photo is developed instantly into a film transparency like an old-school slide.
Okay.
That developed film is then put into the time machine to be sent back and become the object that the camera photographs.
Okay, I'm picturing this. The camera photographs the film that comes out of the machine. The photo is the film. It's a loop.
Right. Now, imagine we just deal with brightness, black or white. Let's say the film coming out is black, so it's opaque. The photo taken will be dark. But in photography, a negative reverses things. So if the object is black, the developed film might be clear, white.
And if the film is clear, the photo will be black.
So if black comes out, white goes in. But if white goes in, black comes out. It feels like a paradox. It's a flip-flop switch, a logical contradiction.
It's the grandfather paradox again, just with film. The existence of black causes white, which negates black.
But Wheeler and Feynman pointed out something crucial. Physics is continuous, not discrete. It's not just binary black or white. There are infinite shades of gray.
Yeah, I see where this is going.
If you plot the brightness of the film entering the machine against the brightness of the film exiting the machine, you have two continuous curves. Calculus, specifically the intermediate value theorem, tells us that if the physics is continuous, those curves must intersect.
They have to cross somewhere.
They have to. There must be a specific shade of mid-gray, let's say 50% gray, that when photographed and developed, produces that exact same shade of 50% gray.
So the universe finds a middle ground, a fixed point, a consistent solution.
Exactly. It's a fixed point theorem. It proves that for continuous physical systems, there is almost always a solution that avoids paradox. The film doesn't flicker between black and white. It settles on gray. Consistency is preserved.
That is actually really reassuring. The universe basically says, I can't do black, I can't do white, so I'll do gray. But the sources mentioned a scenario where this continuity fails, the dial problem.
Yes. This highlights where the solution breaks down. Imagine instead of a camera, we have a dial that can rotate 360 degrees. The machine is set up so that if the dial comes out of the time machine at angle X, the machine mechanically rotates it 90 degrees, so X plus 90, before sending it back in.
Okay, so if it comes out at 12 o'clock, it goes in at 3 o'clock.
Right, and since a circle is continuous, you would think there should be a fixed point. But try to find a number on a circle where X equals X plus 90.
0 becomes 90, 90 becomes 180, 180 becomes 270, 270 becomes 0 again. It never matches.
It never matches. It chases its own tail forever. There is no gray equivalent for a 90-degree rotation.
So what happens? Does the universe explode?
That is the million-dollar question. This suggests that for certain geometries or setups, paradoxes might persist unless the laws of physics simply forbid that specific setup from existing.
So maybe the machine just jams, or the dial breaks.
Or the geometry required to build that machine is impossible in our universe. It's like trying to draw a square circle. The definitions just don't allow it. But where continuity holds, we have solutions. And that brings us to the billiard ball model, which is probably the most concrete proof that you can't change the past, but you can interact with it.
This is Polchinski's paradox. This was one of the deeper dives in the reading. It involves a billiard ball, a wormhole, and a collision.
It is the grandfather paradox in miniature. A billiard ball enters the right mouth of a wormhole, travels back in time, and exits the left mouth in the past. But the trajectory is set up perfectly so that the ball exiting the left mouth is on a direct collision course with its younger self, the ball that is about to enter the right mouth.
So ball A, the older one, knocks ball B, the younger one, away. If ball B is knocked away, it never enters the wormhole.
And if it never enters?
It never exits to knock itself away. Paradox.
Exactly. But researchers Echeverria, Klinkhammer, and Thorne serious physicists sat down and analyzed the equations of motion. They asked, is there any physical way this scenario can play out? And they found something amazing.
They found a loophole.
They found a glancing blow solution. They found that there's a consistent trajectory where the older ball exits the wormhole, but instead of knocking the younger ball completely away, it just clips it. It delivers a slight nudge.
And what does that nudge do?
That nudge alters the younger ball's trajectory just enough so that it enters the wormhole at a slightly different angle. And that new angle is exactly the angle required for it to exit the wormhole and deliver that specific glancing blow.
Wow. So the universe bends over backwards to make the math work. The cause and effect line up perfectly.
It doesn't even bend. It just finds the self-consistent path. It's not magic. It's just that out of all possible trajectories, the only one that can physically happen is the one that causes itself. No paradox, just a weird self-fulfilling trajectory.
It's like the universe is saying, you can try to create a paradox, but I will just adjust the angles until it makes sense.
Precisely. But here's where it gets really interesting. Or, as I like to say, here's where it gets unsettling. We worry about constraints, that we can't kill the grandfather. But the sources point out the opposite problem, underdetermination.
This was a new concept for me. Usually in physics, if I know the speed and position of a ball, I can predict where it goes.
Right. Determinism. But in these time travel models, especially with the billiard balls, researchers found that the glancing blow wasn't the only solution.
There were others.
Sometimes there were infinite solutions. Maybe the ball doesn't hit itself at all. The minimal solution. That's one. Maybe it hits itself once. Maybe it hits itself twice. Maybe it bounces around inside the mouths of the wormhole 10 times before entering. All of these scenarios are mathematically consistent with the initial conditions.
So if I'm standing in the lab about to roll this ball, physics doesn't tell me which future is going to happen.
Exactly. The state of the universe now does not determine the future. This is what we call underdetermination. The present is insufficient to explain what happens next.
That connects back to the unwritten book, doesn't it?
It does. A book could appear from the future. Physics allows for that loop. But physics doesn't tell us which book it is. It could be Hamlet. It could be Harry Potter. It could be a cookbook. It could be a book full of gibberish. There are infinite self-consistent loops, and nothing in the present determines which one manifests.
That implies a strange form of indeterminism. Like, the universe has these phantom possibilities floating around, and for some reason, one of them just is. It feels random.
It's spooky. It suggests that if time travel is possible, we live in a universe that is much less rigid than we thought.
Let's level up to quantum mechanics, because if general relativity is weird, quantum mechanics is just plain rude to our common sense. The sources talk about Deutsch's quantum model. How does that solve the paradoxes?
David Deutsch proposed using mixed states, basically probability distributions, to solve consistency. In classical physics, you're either alive or dead. In quantum physics, you can be in a superposition.
Schrödinger's grandfather.
Essentially, yes. Deutsch argues that a time traveler goes back not to a single fixed past, but to a probabilistic mix. Imagine the traveler goes back with a 50% probability of being in state A and 50% in state B. The interactions play out such that they produce exactly that probability distribution as an output.
So consistency is preserved because the probability distribution matches, even if the specific events seem contradictory.
Right. And this often leans on the many worlds interpretation of quantum mechanics. The idea is that the traveler goes back to a different branch of history.
Yeah.
They travel from world A to world B.
Okay, so I leave my timeline, I go to a parallel timeline, and I kill the grandfather there.
Exactly. In world B, the grandfather dies. That's fine, because the traveler was born in world A. The grandfather in world A is still alive. There's no contradiction because the loop isn't closed in a single timeline. It's a spiral across the multiverse.
That feels like cheating, though. Oh, I didn't kill my grandfather, I killed a grandfather.
It solves the logic, but it kind of ruins the drama.
It avoids the logical paradox, but it opens up a can of worms regarding identity. Are you really time traveling, or are you just hopping dimensions? But there is another quantum aspect that is even more mind-blowing. The concept of easy knowledge or computing with time loops.
This was the part about NP-complete problems, right? Solving impossible math problems instantly. I read this 3 times and I'm still struggling to get my head around it.
It is a theoretical implication of consistent time loops. Suppose you have a computer problem that would take 1,000,000 years to solve, like cracking a massive encryption key or factoring a giant number.
Okay, so it's impossible for a normal computer.
Right. But you have a time machine. So you program your computer with a very specific instruction involving a loop. You tell it, check a random answer. If you find the right answer, send that answer back in time to me right now. If you don't find the answer, send a signal back to shut yourself off before you start.
Wait, walk me through the logic there. The setup forces the universe to avoid a paradox. Let's look at the wrong answer scenario. If the computer picks a wrong answer, it triggers the instruction to send a shutdown command back in time.
So the computer shuts down before it even starts.
But if it shuts down, it never runs the search. If it never runs the search, it never sends the shutdown command. That's a paradox. It's inconsistent.
So the universe cannot allow the computer to pick a wrong answer.
Exactly. The only consistent path history can take, the only glancing blow available, is for the computer to randomly stumble upon the correct answer immediately. If it finds the right answer, it sends the answer back. The loop is closed. Consistency is maintained.
So you are basically blackmailing the universe into giving you the answer. Give me the answer or I'll create a paradox.
That is exactly what it is. It generates easy knowledge. You get the result without the computational work. This clashes violently with our understanding of information theory and thermodynamics. You can't just get information for free. But in a universe with CTCs, apparently you can.
That is wild. It's like using a cheat code on reality. Speaking of cheat codes and decisions, we have to talk about Newcomb's problem. This was in the stack, and at first I didn't see the connection to time travel, but now I do.
Newcomb's problem is a classic dilemma in decision theory, but it is deeply tied to questions of prediction and causality. Here's the setup. A predictor, maybe a time traveler, maybe a supercomputer, maybe God places 2 boxes in front of you. Box A is transparent and has $1,000 in it. You can see the money.
Okay, box A is a sure thing, $1,000.
Box B is opaque. You don't know what's in it. It's either empty or it contains $1 million.
I'm listening.
You have 2 choices. You can take only box B or you can take both boxes.
Why wouldn't I take both? More is better.
Here is the catch. The predictor has already made a prediction about what you will do. This prediction happened yesterday. If the predictor predicted you would take only box B, they put the $1,000 inside it. If they predicted you would take both boxes, they left box B empty.
And how accurate is this predictor?
Let's say 99.9% accurate. Or perfect, for the sake of argument.
Okay, so if I take both, the predictor likely saw that coming, so box B is empty. I walk away with $1,000 from box A.
All right.
But if I take only box B, the predictor likely saw that coming, so box B has the million. I walk away with $1,000,000.
So what do you do?
Well, the one boxer argument seems obvious. I want the million, so I take box B, expected utility.
That is the expected utility argument. But look at it from the two-boxer perspective, the strategic dominance argument. The prediction was made yesterday. The money is already in the box, or it isn't. The predictor has left the room.
Right.
Your choice now cannot change the past. You can't magically make the money appear or disappear. So imagine the million is in box B. If you take both, you get $1 million plus $1,000.
True.
Now imagine the million is not in box B. If you take both, you get $1,000. If you take only box B, you get $0.
So in either physical scenario, whether the money is there or not, taking both boxes gets me more money.
Exactly. That's the logic of dominance. Taking both always yields a better result than taking only B given a fixed state of the world.
This is maddening. One logic says take one box, the other logic says take both.
And here is the time travel connection. If the predictor is a time traveler who saw your choice, then your choice does cause the past. The money is there because you will choose to take only box B.
It loops back to the grandfather paradox. If I try to trick the predictor like, I flip a coin or change my mind at the last second, a perfect time-traveling predictor would have seen the trick.
It questions whether you have free will at all. If the prediction is perfect, is your decision just an illusion generated by your brain state? This is reflexive oddity. It's fatalism wrapped in a game show.
I feel like we're balancing on the edge of a cliff here. Let's pull back to the physical world for a minute, because even if we solve the logic, the sources mention some practical problems that often get ignored in movies, like the duplication paradox.
This is the messy side of time travel. Imagine a man travels back one day to meet himself. There are now two of him. Mass and energy conservation is suddenly a big issue.
Right, the universe suddenly has an extra 80 kilograms of matter. Where did it come from?
And if he does it again, now there are three. If he loops repeatedly, you could fill a room with copies of the same person.
It's like that scene in Austin Powers, but horrifying.
And the identity crisis is real. Who is the real one? They diverge in experience the moment they separate. If the older one dies, does the younger one eventually die in the same spot? Or can they change the loop? If they change the loop, are they even the same person anymore? It forces us to ask what identity even means over time.
It's an HR nightmare, at the very least. And then there's the spatial paradox, which is my favorite ruin the movie fact. I bring this up at parties and people hate me for it.
The teleportation problem. Fiction treats time travel like an elevator. You go down a floor to the past. You step into the machine in New York. You step out in New York just in 1899.
But the Earth is moving.
The Earth is moving very, very fast. It spins at 1,000 miles per hour. It orbits the sun at 67,000 miles per hour. The solar system itself is moving 500,000 miles per hour through the galaxy.
So if you travel back just 6 months in time,
The Earth is on the other side of the sun.
and you are.
You are floating in the vacuum of space, suffocating instantly. Or, if you get the calculation slightly wrong, you materialize inside a mountain or inside the Earth's mantle.
So a time machine must also be a teleportation machine that can calculate complex orbital mechanics to place you safely on the planet's surface.
Exactly. It adds a layer of complexity that makes the garage inventor trope very unlikely. You need a supercomputer just to land on the ground.
So bringing it all together, we have looked at logic, physics, quantum mechanics, and decision theory. Where does this leave us? Is time travel actually possible, or is the universe just too good at stopping us?
This brings us to the Novikov self-consistency principle. This is the synthesis of everything we've discussed. Igor Novikov, a Russian astrophysicist, argued that the probability of any event creating a paradox is zero.
Meaning the universe is rigged.
Meaning the laws of physics are self-enforcing. If you try to shoot your grandfather, the gun will jam, you will slip, you will kill the wrong man. Not because of magic, but because those are the only histories that are consistent with the future you came from.
It implies a lack of free will. It implies that we are just watching a movie that we think we're acting in.
It implies that humans, in a closed time-like curve, are like actors following a script. You feel like you were choosing, you feel the anguish of the decision, but physics restricts your successful actions to only those that match the future. You are constrained.
And that leads to the expert summary from our notes. The tension between being over-constrained and under-constrained.
That is the key takeaway. Time travel doesn't necessarily break logic, but it leads to two extremes. It leads to over-constraint. You can't do certain things, like change the past. You are locked in.
Yeah.
But it also leads to under-constraint. Objects appear with no origin, like the Shakespeare book. Events happen without a clear cause.
So we are stuck between you have no choice and things happen for no reason.
Precisely. And while general relativity says this is logically possible, these constraints, thermodynamics, entropy, information theory, make it physically unlikely for macroscopic objects like us. Electrons might time travel. Humans, probably not. The universe seems to protect itself from the chaos we would bring.
That is probably for the best. I don't think I'm responsible enough to handle the Shakespeare paradox. I'd probably accidentally erase the Beatles or something.
I don't think any of us are.
Before we sign off, I want to leave the listener with a final thought, something to mull over. We talked about the unwritten book, the idea that time travel allows information to exist without an author, if that's possible. What does that say about creativity or discovery?
That's a deep question.
If a melody or a mathematical formula can just exist in a loop, are we creators? Or are we just transcribers of things that have always been? Are we just tuning into a signal that has no source?
And if we live in a universe where time travel is possible, even if we haven't built the machine yet, does that mean the future is already influencing our present? Our aha moments, actually messages from a future self, ensuring the loop stays closed.
Now that is the thought that will keep me up tonight. Check which box you choose before the prediction is made, everyone. Thanks for stepping into the loop with us.
Goodbye.